The Japanese aviators who circled Pearl Harbor on December 7, 1941, believed American carriers were fragile ironworks held together by rivets and overconfidence, floating scrap yards vulnerable to a single well-placed bomb. 6 months later, that conviction would drown in the same Pacific waters, where Japan's carrier supremacy burned into ash. Before we go deeper into how this miscalculation changed the Pacific War forever, make sure to subscribe for more history that actually happened. The contradiction was born in the smoke of treaty negotiations. When diplomats gathered in Washington in 1922 to prevent another arms race, they created the architectural foundation for the most decisive carrier battle in human history. The Washington Naval Treaty imposed strict tonnage limits on capital ships and carriers, establishing a ratio of 5 tons for America and Britain to every 3 tons. For Japan, individual aircraft carriers could displace no more than 27,000 tons, with armament restricted to guns no larger than 8 inches. But the treaty included a crucial exemption: 2 carriers per nation could reach 33,000 tons if converted from incomplete battlecruiser hulls already under construction. This clause was intended to salvage investments in obsolete ship designs. Instead, it created monsters. America chose to convert 2 Lexington-class battlecruisers, vessels originally designed to hunt and destroy, with 16-inch guns at 35 knots. USS Lexington and USS Saratoga emerged from this transformation as paradoxes, carriers wrapped in battlecruiser armor, powered by turbines meant to propel capital ships across oceans. At 888 feet long and displacing over 43,000 tons at full load, they dwarfed every carrier then afloat. Their 7-inch belt armor, inclined 11 degrees for maximum deflection, could theoretically withstand 14-inch shells. Bulkheads at bow and stern matched that thickness. Even the flight deck sat atop a superstructure armored against smaller caliber fire. These were carriers designed to survive battleship engagements, a doctrine left over from an era when aviation was still unproven. Japan faced the same treaty constraints with different materials. The battlecruiser Akagi and battleship Kaga, both laid down under Japan's 8-8 fleet program, were slated for scrapping. Treaty negotiators allowed their conversion. Akagi stretched 855 feet and displaced 42,750 tons fully loaded. Kaga measured 715 feet but was broader in beam and heavier at 43,650 tons. Both received armor schemes inherited from their capital ship origins. Kaga's belt reached 6 inches in places, with internal compartmentalization designed to contain torpedo damage. Yet their design philosophy diverged sharply from American thinking. Japanese naval architects prioritized offensive striking power over defensive resilience. Every ton allocated to protection meant 1 less ton for aircraft, fuel, or ordnance. The result was carriers with impressive armor compared to purpose-built vessels, but with critical vulnerabilities baked into their operational design. The United States Navy, scarred by institutional memory of fires at sea and influenced by stringent damage control studies, developed carriers with survival as a design imperative. When the Yorktown class entered service in the late 1930s, Enterprise, Yorktown, and Hornet, they embodied lessons learned from Lexington and Saratoga. At 809 feet and 25,900 tons, they were smaller than the converted giants, but their internal architecture reflected a philosophy that fire was a carrier's greatest enemy. American designers created open hangars, essentially massive bays that could be opened to the elements via large rolling doors at the sides. This ventilation system served dual purposes. It allowed rapid dispersal of aviation gasoline fumes that could otherwise accumulate into explosive concentrations, and it provided escape routes for blast overpressure in the event of detonations. When a bomb penetrated an American carrier's flight deck, the resulting explosion had room to expand. horizontally out the open hangar sides rather than channeling destructive force into the ship's vitals. It was engineering that traded some structural integrity for survivability. More crucially, the United States Navy institutionalized damage control in ways the Japanese never matched. Damage control was not merely a specialized function relegated to engineering personnel, it was a fundamental responsibility of every sailor aboard. Training began in boot camp and continued through every stage of a sailor's career. By 1941, damage control parties were organized at the division level, with personnel cross-trained in firefighting, shoring, tutoring, and first aid. Equipment lockers were distributed throughout the ship rather than centralized, ensuring teams could respond to damage without having to traverse burning compartments. Portable pumps, firefighting foam, wooden shoring, timbers, and patching materials were staged at dozens of locations. Communication systems included sound-powered telephones that required no electrical power and functioned even when the ship's generators failed. The fuel systems on American carriers incorporated innovations that seemed minor but proved decisive. Aviation gasoline, with its low flashpoint and volatile vapors, was stored in tanks surrounded by seawater-filled voids and protected by armored boxes. But the fuel distribution lines running through the hangars and up to the flight deck represented the greatest fire hazard. American designers installed a carbon dioxide purging system that could flush fuel lines with inert CO2 gas, displacing gasoline and oxygen and rendering the lines non-flammable. Before combat operations, crews activated this system, evacuating fuel from exposed piping and replacing it with gas that could not burn. It was a procedure that took minutes but created a firebreak between the fuel supply and the bombs raining down from above. Japanese carrier design philosophy evolved from different operational assumptions. The Imperial Japanese Navy envisioned carrier warfare as a decisive confrontation in which the first blow would determine victory. Speed of launch, concentration of striking power, and coordination between multiple carrier divisions took precedence over defensive preparations. Hangars were enclosed spaces, fully integrated into the hull structure with armored sides and deck heads. This design improved structural strength and provided better protection against splinters and small-caliber projectiles. It also created enclosed volumes ideal for trapping heat, smoke, and flammable vapors. Ventilation systems existed, but they were not designed to disperse explosive concentrations rapidly. When bombs or torpedoes breached these spaces, the force had nowhere to dissipate. Fuel handling practices compounded the vulnerability. Japanese carriers stored aviation gasoline in armored tanks, but their fuel lines lacked the purging system standard on American vessels. During flight operations, fuel flowed through kilometers of piping that snaked through hangars and service areas. When combat damage ruptured these lines, gasoline sprayed into enclosed spaces, creating vapor clouds that would ignite from any spark or flame. Damage control doctrine assigned responsibility to specialized engineering personnel rather than distributing it across the crew. These teams were highly trained, but they were also small and could be wiped out by a single bomb hit. Without redundancy in personnel or equipment, a carrier's ability to fight fires and control flooding depended on the survival of a handful of men and centralized gear lockers. The disparity remained theoretical until tested by battle. In early 1942, Japan's Kido Butai, the mobile force, was the most powerful naval aviation formation ever assembled. 6 fleet carriers operating as a unified strike force had demonstrated their dominance at Pearl Harbor, where they launched over 350 aircraft in coordinated waves that devastated the U.S. Pacific Fleet. The attack sank or crippled 8 battleships, destroyed 188 aircraft, and killed 2,403 Americans. For Japan, it validated a decade of carrier warfare development and confirmed that American defenses were as fragile as their intelligence suggested. Japanese aviators returned with reports of success so overwhelming that planners began to believe their own propaganda, that American carriers, if they could even be found, would collapse under similar assault. The battles of Coral Sea in May 1942 and Midway in June 1942 shattered those assumptions with data written in fire and steel. At Coral Sea, USS Lexington and USS Yorktown engaged Japanese carriers. Shokaku and Zuikaku in the First Naval Battle fought entirely by carrier aircraft, where the opposing surface ships never came within sight of each other. Lexington absorbed 2 torpedo hits and 2 bomb strikes. The torpedoes ruptured fuel tanks and aviation gasoline lines. Fires erupted almost immediately, but damage control teams contained them within an hour. Portable pumps countered flooding, and the carrier resumed flight operations. For nearly 2 hours after the attack, Lexington operated normally, recovering aircraft and preparing for further strikes. But gasoline vapors from ruptured fuel lines had accumulated in unventilated void spaces deep below the hangar deck. At 12:47 p.m., a spark ignited the vapors. The explosion lifted the flight deck and destroyed the fire suppression systems. Secondary fires spread beyond control, detonating ordnance and igniting fuel tanks. By evening, Lexington was a roaring inferno beyond saving. She was scuttled by American destroyers. After her crew abandoned ship, Lexington's loss taught American carrier forces brutal lessons about fuel vapor management, but it also demonstrated the resilience built into their damage control systems. Despite catastrophic damage that would have destroyed lesser vessels within minutes, Lexington remained operational for 2 hours. After the initial torpedo and bomb hits, her crew fought fires, repaired systems, and continued flight operations during a window when many vessels would have already sunk. The real killer was not the Japanese attack but an insidious accumulation of gasoline vapor in spaces that lacked proper ventilation, a design flaw, but one that existed in spaces outside the primary hangar volume. Yorktown's performance at Coral Sea revealed how effective American damage control could be when systems functioned as designed. An 800-kilogram bomb penetrated the flight deck near the island and detonated in the hangar, rupturing fuel lines and igniting fires. 66 men died instantly. Flames spread across the hangar deck, threatening ammunition stores and parked aircraft. But the hangar's open sides vented much of the blast force overboard, and the CO2 purging system prevented fuel lines from feeding the flames. Damage control parties surrounded the fires with foam and seawater, then used portable pumps to wash burning gasoline over the side through the open hangar doors. Within 30 minutes, fires were contained. Within 2 hours, Yorktown resumed air operations at reduced capacity. The bomb had caused structural damage that would require shipyard repair, but it had not crippled the carrier's ability to fight. The Japanese carriers at Coral Sea experienced vastly different outcomes. Shokaku took 3 bomb hits that penetrated her flight deck, detonating in the enclosed upper hangar. Fires erupted immediately, fueled by aviation gasoline and munitions. Damage control teams responded, but the enclosed hangar trapped heat and smoke, making it nearly impossible to approach the flames. Shokaku's fire suppression systems lacked the capacity to flood entire compartments with CO2, and her crew did not have the training or distributed equipment to contain multiple fires simultaneously. The carrier survived because her engineering spaces remained intact and her captain ordered immediate withdrawal from the combat zone, but she was out of action for months. Zuikaku escaped damage, but her aircrew losses were severe enough to prevent participation in the upcoming Midway operation. When Yorktown limped into Pearl Harbor on May 27, 1942, Navy engineers estimated repairs would Take 3 months at a minimum. The Coral Sea bomb had destroyed 10 compartments, warped the flight deck, and damaged internal bulkheads. Admiral Chester Nimitz gave the shipyard 3 days. The reason was simple: intercepted Japanese radio traffic indicated an imminent attack on Midway Atoll. And Nimitz needed every carrier he could muster. What followed was one of the most remarkable feats of emergency repair in naval history. 1,400 shipyard workers swarmed Yorktown around the clock. Welders closed rents in the flight deck with steel plates. Carpenters shored damaged bulkheads with timber bracing. Electricians spliced severed power cables and communication lines. Machinists fabricated replacement parts for systems that could not be cannibalized from other ships. The work proceeded under floodlights through the night, every worker aware that men would die if the carrier did not sail. Rolling blackouts dimmed Honolulu so the shipyard could draw full power. Supplies came by truck from every depot on Oahu. The work was not perfect. Some repairs were temporary patches held by bolts and prayer. Compartments that should have been gutted and rebuilt were instead sealed off and abandoned. But after 72 hours, Yorktown steamed out of Pearl Harbor with over 100 civilian repair workers still aboard, continuing their work as the carrier raced northwest toward Midway. The Japanese combined fleet approaching Midway in early June 1942 represented the apex of Japanese carrier power. Vice Admiral Chuichi Nagumo commanded the Kido Butais for fleet carriers Akagi, Kaga, Soryu, and Hiryu. Together they embarked 248 aircraft and were crewed by the most experienced carrier aviators in the world. These were the same ships and men who had struck Pearl Harbor 6 months earlier. They had operated continuously since then, hitting targets from Darwin to Colombo, sinking British heavy cruisers and a carrier, and bombing Allied bases across the Pacific and Indian Oceans. Their record was unblemished. Nagumo's force sailed toward Midway expecting to annihilate the island's defenses, draw out the American carriers, and destroy them in a single decisive engagement. American intelligence, however, had provided Admiral Nimitz with the Japanese battle plan in granular detail. Cryptanalysts at Station HYPO in Pearl Harbor had broken portions of the Japanese naval code, identifying Midway as the target and predicting the attack date. Nimitz positioned his 3 available carriers, Enterprise, Hornet, and the hastily repaired Yorktown, northeast of Midway, beyond the range of Japanese reconnaissance but within striking distance once Nagumo revealed his position by attacking the atoll. It was a gamble built on intelligence intercepts and the hope that American carriers could deliver a knockout blow before the Japanese even knew they were there. June 4, 1942, began with Nagumo launching 108 aircraft against Midway at 4:30 a.m. The strike included bombers, fighters, and torpedo planes tasked with suppressing the island's defenses before the planned amphibious landing. Nagumo retained a second wave aboard his carriers, 93 aircraft armed with torpedoes and armor-piercing bombs intended for use against American ships, should any appear. This reserve represented standard doctrine: maintain a strike force ready to respond to the unexpected. The decision would haunt Japanese naval aviation for generations. American patrol planes spotted the Kido Butai at 5:45 a.m., and Midway's defenders scrambled every available aircraft to intercept the Japanese strike and launch their own counterattack. Midway's planes were obsolete and undermanned, but they forced Nagumo to keep his fighters close to defend the carriers. At 7 a.m., the strike leader radioed that Midway required a second attack to fully suppress its defenses. Nagumo faced a choice: his reserve aircraft were armed for anti-ship operations with torpedoes and heavy bombs, weapons ill-suited to attacking land targets. Ordering a rearming meant bringing aircraft below to the hangars, removing torpedoes, replacing them with high-explosive bombs. and then respotting the planes on the flight deck, a process requiring at least an hour. But no. American carriers had been reported, and Midway's defenses were still launching aircraft. Nagumo ordered the rearming. At 7:28 a.m., a Japanese scout plane radioed the report that Nagumo dreaded American ships sighted to the northeast. The message was vague, no indication of ship types or numbers, but it shattered the operational calculus. Nagumo suspended the rearming order and waited for clarification. Minutes stretched into a quarter hour. At 7:45 a.m., the scout confirmed sighting one carrier. Nagumo reversed his order, rearm the reserve aircraft with torpedoes and armor-piercing bombs for an anti-ship strike. Now the hangars became chaotic workshops as ordnance crews hustled to undo what they had just begun. Torpedoes were remounted. Bombs were moved to storage. Aviation fuel hoses snaked across the decks as aircraft were topped off for the strike. The hangars filled with volatile ordnance, fuel, vapors, and bustling personnel. Meanwhile, American torpedo squadrons from Yorktown, Enterprise, and Hornet had located the Kido Butte and were pressing home attacks with obsolete TBD Devastator torpedo bombers. These aircraft were slow, poorly armed, and required long, straight attack runs that made them easy prey for Japanese fighters and anti-aircraft fire. The attacks were slaughtered. Torpedo Squadron 8 from Hornet lost all 15 aircraft. Torpedo Squadron 3 from Yorktown lost 10 of 12. Torpedo Squadron 6 from Enterprise lost 10 of 14. Not a single American torpedo found its target. But the attacks achieved something unintended. They pulled Japanese combat air patrol down to wave-top altitude, forcing the Zeros to chase and destroy every lumbering torpedo plane. The sky above the Japanese carriers was left exposed. At 10:22 a.m., Lieutenant Commander Clarence Wade McCluskey, leading Enterprise's dive bomber squadrons, arrived over the Kido Butte at 19,000 feet. Below him, Akagi, Kaga, and Sarayu were turning into the wind to launch their strike against the American carriers. Their decks were crowded with armed and fueled aircraft. McCluskey split his force. Scouting Squadron 6 attacked Kaga. Bombing Squadron 6 targeted Akagi. Simultaneously, Yorktown's Bombing Squadron 3, led by Lieutenant Commander Maxwell Leslie, rolled into dives on Sarayu. The attack was uncoordinated by plan but synchronized by chance. The three carriers were struck within 5 minutes. Akagi took a single 1,000-pound bomb that penetrated the flight deck near the amidships elevator and detonated in the upper hangar. The bomb struck amidst fully fueled and armed aircraft awaiting launch. Aviation gasoline ignited instantly. Torpedoes cooked off. The enclosed hangar trapped the explosions, channeling force downward through the lower hangar and outward through bulkheads never designed to contain such pressure. Fires spread into ordnance magazines, detonating stored bombs and torpedoes. Within minutes, Akagi's firefighting capacity was overwhelmed. Damage control teams could not approach the flames due to heat and secondary explosions. Admiral Nagumo evacuated to a cruiser. By mid-afternoon, Akagi was a gutted wreck, fires burning uncontrollably. She was scuttled by Japanese destroyers early on June 5 to prevent capture. Kaga absorbed 4 1,000-pound bombs in rapid succession. 2 hit the flight deck forward, penetrating into the upper hangar where aircraft were being fueled and armed. A third struck near the island superstructure, destroying the bridge and killing most senior officers. The fourth hit aft, rupturing aviation gasoline tanks. Fires erupted across the length of the ship. Fuel lines ruptured by the bomb hit sprayed gasoline into the fires, feeding an inferno that spread faster than damage control teams could respond. Kaga's enclosed hangars became blast furnaces. Ordnance detonations began. Almost immediately, her captain ordered abandon ship at 4:25 p.m. Kaga sank at 7:25 p.m. after. Internal explosions broke her keel. Soryu took 3 1,000-pound bombs in the span of 2 minutes. All 3 penetrated the flight deck and detonated in the hangars. The first hit forward, igniting parked aircraft. The second struck amidships, rupturing fuel lines and detonating ordnance. The third hit aft, destroying fire suppression systems and cutting damage control communication lines. Soryu's fires spread uncontrollably within 10 minutes. Her damage control officer and most of his team were killed in the initial blasts. Without leadership or equipment, the crew could not contain the flames. Soryu was abandoned at 7:15 p.m. and sank the following morning. The fourth carrier, Hiryu, escaped the initial attack and launched 2 retaliatory strikes against Yorktown. Hiryu's bombers and torpedo planes found the American carrier and inflicted severe damage. 3 bombs struck Yorktown, penetrating the flight deck and exploding in the hangar. 1 bomb ruptured the uptakes from the boilers, venting smoke into the engineering spaces and forcing a shutdown of 6 boilers. Yorktown slowed to 6 knots. But the CO2 purging system had evacuated fuel lines before the attack, and the open hangar sides vented much of the blast force overboard. Damage. Control teams contained fires within 40 minutes. Engineers cross-connected boiler systems and relit fires, restoring power. By 1:40 p.m., Yorktown was making 20 knots and recovering aircraft. Then Hiryu's torpedo bombers arrived. 2 torpedoes struck Yorktown's port side, rupturing fuel tanks and flooding machinery spaces. The carrier lost power and developed a severe list. Despite heroic efforts by damage control parties, including counter-flooding to correct the list and portable pumps to control flooding, Yorktown was dead in the water. Her crew abandoned ship, expecting her to sink. She did not. Yorktown remained afloat, and the next day salvage crews reboarded to attempt to tow to Pearl Harbor. On June 6, Japanese submarine I-168 found the drifting carrier and put 2 more torpedoes into her. Yorktown capsized and sank on June 7, 3 days after taking her first damage. But Hiryu's triumph was short-lived. Dive bombers from Enterprise found the last Japanese carrier at 5 p.m. on June 4. 4 1,000-pound bombs hit Hiryu, 3 penetrating the flight deck and detonating in the hangars. The same sequence repeated, ignited aviation fuel, exploding ordnance, spreading fires, overwhelmed damage control. Hiryu burned through the night. She was scuttled on the morning of June 5. In the span of 6 minutes on the morning of June 4, from 10:22 to 10:28 a.m., 3 Japanese fleet carriers were mortally wounded. A 4th followed that evening. The Kido Butai, which had dominated the Pacific for 6 months, ceased to exist as a fighting force. Japan lost 3,057 men, including many of her most experienced pilots and aircrew. The 4 carriers represented half of Japan's first-line carrier strength. Replacing the ships would take years, replacing the pilots and their accumulated experience would prove impossible. The destruction was not due to superior American aircraft or tactics. The TBD Devastator was obsolete. The F-4F Wildcat fighter outclassed by the Zero, and the SBD Dauntless dive bomber merely competent. American carrier doctrine was still evolving, and coordination between squadrons was poor. What decided the battle was a conjunction of intelligence, timing, and engineering. American cryptanalysts provided Nimitz the knowledge to position his carriers for ambush. American torpedo squadrons, though slaughtered, forced Japanese fighters low and created a window for the dive bombers. And When American bombs hit Japanese carriers, those carriers died because their design and damage control doctrine could not contain the resulting fires. Japanese carriers at Midway were caught at their most vulnerable moment, rearming aircraft, flight decks crowded with fueled and armed planes, hangars filled with ordnance and fuel vapors. But that vulnerability was not accidental. It was the product of design choices made years earlier. Enclosed hangars maximized structural strength but trapped explosive force. Fuel systems lacked purging mechanisms to render lines inert. Damage control was centralized among specialists who could be wiped out by a single bomb. Ventilation systems could not rapidly disperse gasoline vapors. Ordnance handling procedures prioritized speed of operations over safety margins. Each decision made sense within its context, but together they created carriers that could be destroyed by the very striking power they were designed to deliver. American carriers, by contrast, survived damage that would have sunk vessels built differently. Yorktown absorbed 3 bombs and 2 torpedoes at Midway and remained afloat for 3 days, requiring a submarine to finish her. At the Battle of the Eastern Solomons 2 months later, Enterprise took 3 bomb hits that killed 74 men and destroyed her forward elevator. Fires erupted across the hangar deck, but damage control parties contained them within an hour. The carrier resumed flight operations that afternoon. At the Battle of Santa Cruz in October 1942, Enterprise took 2 bombs and a damaged aircraft that crashed into her flight deck. Fires ignited. Fuel lines were ruptured. The forward elevator was destroyed. Damage control teams extinguished the fires, patched the flight deck with steel plates, and restored limited operations within minutes. Enterprise remained in action throughout the battle. Hornet, by contrast, took 4 bombs, 2 torpedoes, and 2 kamikaze hits at Santa Cruz and was abandoned only after damage control teams had exhausted every option, and even then, she remained afloat long enough that American destroyers had to scuttle her with torpedoes and gunfire. The contrast extended beyond engineering to doctrine and training. American carriers operated under the assumption that damage would occur and survival depended on every sailor's ability to respond. Japanese carriers operated under the doctrine that the best defense was overwhelming offense. Strike first, strike hard, and destroy the enemy before they could retaliate. When that doctrine failed at Midway, Japanese carriers had no fallback. Their damage control systems were not redundant, their crews not cross-trained, their equipment not distributed. When the bombs hit, the systems designed to save the ships could not function because the men and materials needed were already burning. Japan did learn from Midway, but the lessons came too late and were incompletely applied. The carrier Taiho, commissioned in 1944, incorporated armored flight decks and improved subdivision to contain damage. But her hangars remained enclosed, and her fuel systems lacked adequate vapor management. At the Battle of the Philippine Sea in June 1944, Taiho took a single torpedo from the submarine USS Albacore. The torpedo ruptured aviation fuel tanks, and gasoline vapor spread through the enclosed hangars. A damage control officer, unfamiliar with proper ventilation procedures, ordered all ventilation systems activated to disperse the fumes. Instead, the fan spread gasoline vapor throughout the ship. Hours later, a spark ignited the vapor cloud. The resulting explosion ripped Taiho apart from within. She sank with 1,650 men, killed not by enemy action but by a design philosophy that had never fully corrected the vulnerabilities exposed at Midway. American carriers continued to refine their damage control systems throughout the war. The Essex-class carriers, commissioned from 1943 onward, incorporated lessons from every battle. Hangar fire suppression systems were upgraded with foam generators and sprinkler arrays. Fuel systems Included automatic shut-off valves that activated when lines were ruptured. Damage control lockers were increased in number and distributed to ensure no single hit could eliminate all firefighting. Equipment. Crew training intensified, with every sailor required to qualify in damage control basics. The results were evident. Essex-class carriers absorbed kamikaze strikes, bomb hits, and torpedo damage that would have destroyed earlier vessels, yet continued fighting. USS Franklin, hit by 2 armor-piercing bombs while her hangar was full of armed and fueled aircraft, suffered over 800 dead. And was nearly lost, but damage control teams kept her afloat, and she limped back to the United States under her own power, a burnt-out hulk that nonetheless survived because her crew refused to give up and her design gave them the tools to fight. The narrative that American carriers were fragile targets, floating scrap vulnerable to Japanese prowess, was born from pre-war prejudice and early war Japanese success. It died at Midway, incinerated by fires that Japanese carriers could not extinguish. The belief that American engineering was inferior, that American sailors lacked the spirit of Japanese warriors, that American carriers could not withstand the striking power of the Kido Butai, all of it dissolved in the same flames that consumed Akagi, Kaga, Soryu, and Hiryu. The reality was that American carriers were over-engineered for survival, designed by men who feared fire more than enemy fleets and who understood that a carrier's value lay not in its ability to launch a devastating first strike, but in its ability to continue fighting after absorbing damage that would have killed lesser ships. Japan's carrier doctrine prioritized the decisive battle, the single engagement that would cripple the enemy's will to fight. It was a philosophy rooted in the success at Tsushima in 1905, where the Japanese fleet annihilated a Russian armada in a single day. Carriers were designed to deliver that kind of overwhelming blow. But carrier warfare was not battleship warfare. Carriers were fragile in ways battleships were not. They carried thousands of tons of aviation fuel and explosives. They operated aircraft that required constant fueling and arming. Their hangars were workshops filled with flammable materials and volatile ordnance. A carrier that could not contain damage was a carrier that could not survive modern combat. American carrier doctrine evolved from different lessons. The U.S. Navy had never fought a decisive fleet engagement. Its institutional memory was shaped by convoy protection, commerce raiding, and the grinding attrition of World War I. When American naval architects designed carriers, they designed them for sustained operations in hostile environments where damage was inevitable. They over-engineered the damage control systems, distributed firefighting equipment redundantly, trained every sailor in basic firefighting, and accepted weight penalties and reduced aircraft capacity in exchange for survivability. It was not glamorous. It did not produce a more effective first strike. But it meant that American carriers could absorb punishment, recover, and continue fighting in ways that Japanese carriers could not. The Battle of Midway was decided in those 5 minutes when American dive bombers struck 3 Japanese carriers simultaneously. But the outcome was determined years earlier, in the design rooms, where engineers chose between offensive power and defensive resilience, in the training schools where damage control became every sailor's responsibility, in the doctrinal debates where admirals argued whether carriers should be sword or shield. Japan chose the sword. America chose both, and accepted that the shield was more important. When the two philosophies collided at Midway, the results were written in fire and wreckage. The lessons of Midway extended far beyond the immediate tactical victory. Japan lost the strategic initiative in the Pacific. Her carrier fleet, which had terrorized Allied forces from Hawaii to Ceylon, was crippled in a single day. Replacing the ships was possible, though difficult under wartime industrial constraints. Replacing the pilots, maintainers, and aircrew was not. Japan's carrier aviators in June 1942 were veterans with thousands of hours of flight time and months of combat experience. They were irreplaceable. When they died at Midway, in the fires that consumed their carriers and in the battles that followed, Japan's ability to wage carrier warfare died with them. New carriers would enter service, but they would be crewed by novices learning in combat, facing American pilots whose training only improved as the war progressed. The industrial mobilization that produced America's carrier fleet represented a transformation unprecedented in scale and speed. When the Essex-class design was finalized in 1940, American shipyards had limited experience with carrier construction. Only 7 fleet carriers had been completed, and most were conversions or one-off designs. The Essex class would be the first standardized fleet carrier class built in large numbers. The design incorporated every lesson learned from earlier carriers: longer flight decks to accommodate heavier aircraft, improved armor protection around magazines and machinery spaces, enhanced anti-aircraft batteries, and distributed damage control equipment. Most critically, the design was modular, with major components prefabricated in sections that could be assembled rapidly at multiple shipyards. American industry attacked carrier production with methods borrowed from mass manufacturing. Prefabrication allowed hull sections, deck assemblies, and superstructure components to be built simultaneously at different locations and then transported to the final assembly yard for integration. Electric welding, which had been controversial in the 1930s due to concerns about quality control, became standard because it was faster and required less skilled labor than riveting. Shipyards trained tens of thousands of workers, many of them women entering industrial work for the first time, in welding, fitting, and assembly techniques. Quality inspectors used X-ray equipment to check welds for defects, ensuring that speed did not compromise structural integrity. The result was a production tempo that astounded observers. USS Essex, the class name ship, required 20 months from keel laying to commissioning. USS Lexington, CVE-16, the second ship, required 19 months. By 1943, yards were completing Essex-class carriers in 15 to 16 months. The ships emerged not as unique creations but as standardized products, each virtually identical to her sisters, simplifying maintenance, training, and spare parts logistics. This standardization meant that a sailor trained on one Essex-class carrier could transfer to another and immediately know where every piece of equipment was located and how systems operated. Damage control parties could use the same procedures on any ship in the class. Replacement parts were interchangeable. It was industrial warfare applied to naval construction, and it worked. America's carrier fleet, by contrast, expanded exponentially. The Essex-class carriers arrived in 1943, followed by the smaller but numerous Independence-class light carriers converted from cruiser hulls. By 1945, the United States had over 24 fleet and light carriers operational in the Pacific, supported by dozens of escort carriers providing air cover for amphibious landings and convoy protection. Japan managed to commission a handful of new carriers, but fuel shortages, pilot attrition, and overwhelming American air superiority rendered them ineffective. By 1944, Japanese carriers were reduced to decoys, sailing without sufficient aircraft or pilots, tasked with drawing American forces away from more critical targets. The doctrinal shift in American carrier operations after Midway was equally significant. Pre-war doctrine had envisioned carriers operating independently or in pairs, avoiding decisive engagements with enemy battle fleets. Midway demonstrated that massed carrier forces could deliver knockout blows if properly coordinated. American carrier doctrine evolved toward the fast carrier task force concept, multiple carriers operating as a unified formation, protected by cruisers and destroyers. capable of projecting overwhelming air power across hundreds of miles. This formation became the primary offensive weapon of the Pacific War, striking Japanese bases, supporting amphibious landings, and eventually bringing the war to Japan's home islands. Japanese carrier operations after Midway were characterized by caution and diminishing effectiveness. The loss of 4 carriers and their air groups forced a defensive posture that Japan's offensive-oriented doctrine was ill-suited to execute. Subsequent carrier battles, Eastern Solomons, Santa Cruz, Philippine Sea, saw Japanese carriers achieving tactical successes but suffering attrition they could not replace. At the Battle of the Philippine Sea in June 1944, Japan launched Operation Ago, a desperate attempt to destroy American carrier forces covering the invasion of Saipan. The battle became known as the Great Marianas Turkey Shoot as American fighters, aided by radar direction and overwhelming numbers, annihilated Japanese air strikes. Japan lost 3 carriers and over 600 aircraft. American losses were minimal. The disparity was not due to inferior Japanese pilots alone, it was the cumulative result of attrition that began at Midway, where Japan lost not just ships but the irreplaceable core of experienced personnel needed to train successors. The sinking of Yorktown at Midway, though a tactical loss, reinforced American confidence in carrier survivability. Yorktown absorbed bomb and torpedo damage that would have destroyed a Japanese carrier within minutes, yet she remained afloat and operational for extended periods after each hit. Her eventual sinking required multiple attacks over several days. The carrier's resilience demonstrated that American design philosophy worked. It validated the weight allocated to armor, the complexity of damage control systems, and the training invested in every sailor. When Enterprise and Hornet survived similar damage in later battles, the lesson was reinforced: American carriers could be hit hard and keep fighting. The individual stories of men who fought at Midway illustrate the human dimension of decisions made in design offices years before. Ensign George Gay, the sole survivor of Torpedo Squadron 8, watched from the water as the Japanese carriers burned. He had launched from Hornet with 14 other TBD devastators, flying low and slow toward the Japanese fleet while Zeros swarmed around them. One by one, his squadron mates were shot down. Gay's aircraft took multiple hits, his gunner was killed, and he ditched into the ocean near the Japanese carriers. For hours he floated, hiding under a seat cushion when Japanese ships passed nearby, witnessing the destruction of Akagi, Kaga, and Sarayu from a perspective no other American shared. His survival was luck, but it was also the result of American training that emphasized ditching procedures and survival techniques. Japanese pilots, trained to fight to the death, rarely survived being shot down over water because they lacked the emphasis on survival that American training provided. Chief Aviation Machinist's mate John William Finn, stationed at Naval Air Station Kaneohe during the Pearl Harbor attack, exemplified the damage control mindset that pervaded American naval culture. When Japanese aircraft strafed his base, Finn mounted a machine gun on an exposed platform and returned fire despite being wounded multiple times. He continued fighting for over 2 hours, shooting down at least 1 Japanese aircraft and inspiring other personnel to resist. His actions earned him the Medal of Honor, but more importantly, they demonstrated the principle that every sailor was responsible for fighting back, regardless of their specialty or assignment. This mentality, that damage control and defense were everyone's job, became institutionalized in American carrier operations and proved decisive when ships were hit and damage control parties needed immediate reinforcement from anyone available. The Japanese carrier crews at Midway faced impossible situations with discipline and courage, but their training and systems failed them when fires spread beyond control. On Akagi, Captain Taihiro Aoki remained aboard organizing firefighting efforts even as explosions tore through the hangar decks. His Damage control teams fought valiantly, but they lacked the distributed equipment and cross-trained personnel to contain fires in multiple locations simultaneously. When the order finally came to abandon ship, hundreds of men were already trapped below decks by flames and smoke. Many died not from enemy action but from the structural design that provided no adequate escape routes from lower compartments once the hangar areas were engulfed. American carriers, with their multiple exit routes, an emphasis on rapid evacuation when necessary, gave crews better chances of survival even when the ship was doomed. The after-action reports filed by American carrier captains following Midway contained detailed analyses of what worked and what failed, recommendations for equipment improvements, and candid assessments of tactical errors. Captain Elliot Buckmaster of Yorktown noted that the CO2 fuel line purging system had prevented catastrophic fires despite multiple bomb hits, validating the Navy's investment in this technology. He recommended expanding CO2 systems to cover more areas of the ship and installing automatic activation mechanisms that would purge fuel lines immediately upon detecting explosions or fires. These recommendations were implemented in subsequent carriers and retrofit into existing vessels. The feedback loop between combat experience and design improvement was rapid and effective, allowing the Navy to continuously refine its carriers based on what sailors learned in battle. Japanese after-action reports, by contrast, focused on tactical decisions and crew performance rather than systemic design issues. The emphasis was on what individuals had done wrong rather than what systems had failed. This reflected cultural factors. Japanese military culture discouraged criticism of institutional decisions and emphasized personal responsibility, but it also meant that fundamental vulnerabilities in carrier design were not addressed because they were not explicitly identified as problems. The enclosed hangars, the lack of fuel line purging systems, the centralized damage control organization, these features were not questioned because doing so would imply that senior leaders had made poor decisions years earlier. Instead, the focus was on improving crew training and fighting spirit, solutions that could not overcome engineering inadequacies. The human cost at Midway was severe but disproportionate. American losses totaled 307 dead, including most of the torpedo bomber crews who gave their lives in attacks that achieved no direct hits, but enabled the dive bombers' success. Japanese losses exceeded 3,000 dead, most of them trapped aboard burning carriers or killed when their aircraft were shot down during futile attempts to attack American ships after their own carriers were destroyed. The disparity reflected not just the battle's outcome but the differing philosophies underlying each Navy's approach to damage control and crew survivability. American doctrine emphasized abandoning ship only when all hope of saving her was lost, and even then, rescue operations prioritized recovering every sailor possible. Japanese doctrine emphasized fighting to the end, often resulting in needless deaths when carriers were clearly doomed. But orders to abandon ship came too late or not at all. The immediate aftermath of Midway saw both navies reassessing their carrier doctrines in light of what the battle had revealed. For the United States Navy, the lesson was clear: massed carrier strikes could overwhelm even the most experienced enemy, provided intelligence-enabled proper positioning and coordination could be achieved. The challenge was improving that coordination. At Midway, American squadrons had attacked piecemeal, arriving over the Japanese carriers at different times due to navigation errors and differing speeds of aircraft types. The torpedo bombers arrived first and were slaughtered, but their sacrifice created the opportunity for dive bombers to strike unopposed. This sequence was accidental rather than planned. American carrier doctrine needed to evolve toward coordinated strikes where fighters, dive bombers, and torpedo planes arrived simultaneously, with fighters suppressing enemy combat air patrol while bombers attacked from multiple axes. The United States Navy also recognized that radar-directed fighter interception had proven decisive in defending carriers from attack. Yorktown's radar had detected incoming Japanese strikes at distances exceeding 50 miles, providing time to launch fighters and vector them to intercept. The British had developed radar fire control systems that allowed anti-aircraft guns to engage aircraft beyond visual range, and the United States Navy began adapting these systems for carrier operations. By 1943, American carriers embarked combat information centers where radar operators, fighter directors, and gunnery officers worked in integrated teams to coordinate defense. This centralized command and control, combined with proximity-fused anti-aircraft shells that exploded near targets rather than requiring direct hits, transformed carrier defense from a desperate last stand into a systematic destruction of incoming raids. Japanese naval leadership drew different conclusions from Midway, conclusions that reflected institutional biases and strategic constraints. The official after-action reports attributed the defeat to bad luck and tactical errors by Admiral Nagumo rather than systemic problems with carrier design or doctrine. The decision to rearm aircraft for a second strike on Midway was criticized, but the underlying assumption that carriers should prioritize offensive striking power over defensive resilience remained unchallenged. Japanese naval architects did begin designing carriers with improved armor and subdivision, but these improvements focused on protecting against bomb hits rather than addressing the fire and vapor management issues that had proven so catastrophic. The result was carriers like Taiho and Shinano, which incorporated heavy armor but retained enclosed hangars and inadequate damage control systems. The pilot attrition Japan suffered at Midway compounded in every subsequent battle. Japan's naval aviation training program had produced superbly skilled pilots before the war, but the program required years to turn recruits into carrier-qualified aviators. Pilots needed hundreds of hours of flight time, extensive gunnery and bombing practice, and experience operating from carrier decks, training that consumed enormous quantities of fuel and aircraft. As Japan's fuel supplies dwindled due to submarine interdiction of tankers, training hours were cut. As aircraft production struggled to replace combat losses, training units received older, worn-out planes that were more dangerous to fly than enemy fighters. By 1944, Japanese carrier pilots were entering combat with fewer than 100 hours of total flight time, facing American pilots with 3 or 4 times that experience. The inevitable result was massacre. At the Battle of the Philippine Sea, American fighter pilots described Japanese attackers as so inexperienced they could be shot down almost effortlessly. The strategic implications of Midway resonated through the remainder of the Pacific War. Japan's offensive capability was broken. The planned invasion of Midway was abandoned, and with it, Japan's hope of extending her defensive perimeter far enough to make American counterattack prohibitively costly. The initiative passed to the United States. Within 2 months, American forces landed on Guadalcanal, beginning a grinding campaign up the Solomon Islands chain. Each subsequent battle saw American forces growing stronger while Japanese forces weakened through attrition. The industrial and demographic advantages that Japan had hoped to neutralize through quick victories and a negotiated peace became insurmountable as the war dragged on. Midway's legacy in naval architecture was equally profound. Post-war carrier design worldwide incorporated the lessons learned from the battle. Enclosed hangars fell out of favor except where armored flight decks necessitated them, and even then, ventilation and vapor management systems became standard. Damage control evolved from a specialized function to a fundamental aspect of ship design and crew training. Fuel systems incorporated multiple redundancies and automatic shutoff mechanisms. Firefighting equipment was distributed throughout vessels rather than centralized. The concept that every sailor was a damage control technician became doctrine in the United States Navy and influenced naval training programs globally. The Japanese carriers that burned at Midway were not poorly designed ships. Akagi, Kaga, Soryu, and Hiryu were products of a coherent design philosophy that prioritized offensive striking power and accepted vulnerability as the price of that capability. In a war decided by single decisive battles, that philosophy would have been vindicated. But carrier warfare proved to be a prolonged attrition struggle, in which survival mattered as much as striking power. Ships that could absorb damage and continue fighting had strategic value far exceeding ships that could deliver devastating blows but could not survive retaliation. American carriers embodied that principle. Japanese carriers did not, and at Midway, the consequences became undeniable. The perception of American carriers as inferior was reinforced by pre-war observations of their construction methods. Japanese naval attaches who visited American shipyards in the 1930s reported that American carriers appeared hastily built, with extensive use of welding rather than riveting, lighter scantlings in non-critical areas, and less attention to finish details. These observations were accurate but misleading. American shipbuilding had adopted electric arc welding earlier and more extensively than Japanese yards, a transition driven by cost considerations and speed of construction. Welded seams were actually stronger and more watertight than riveted joints, though they required skilled welders and careful quality control. The lighter structural members observed in American carriers were the result of engineering calculations that optimized strength-to-weight ratios rather than simply overbuilding every component. And the less polished finish reflected American industrial culture, which prioritized function over form and accepted that warships would be battered in service regardless of how pristine they looked at commissioning. Japanese carriers, by contrast, were built with meticulous attention to detail and finish. Akagi and Kaga featured beautifully crafted interiors, with polished brass fittings, varnished wood paneling in officer spaces, and carefully fitted compartments. This reflected both Japanese craftsmanship traditions and the cultural importance placed on aesthetic excellence. But it also revealed a misallocation of effort. The brass fittings that looked impressive in port became shrapnel in combat. The wooden paneling burned. The carefully fitted compartments, while structurally sound, sometimes complicated damage control by creating odd angles and corners where equipment could not easily maneuver. American carriers, with their more utilitarian construction, sacrificed appearance for functionality. Their equipment lockers were accessible from multiple directions. Their compartments had standardized fittings that allowed quick replacement. Their systems were designed for maintenance by ordinary sailors rather than requiring specialized technicians. The industrial contexts in which American and Japanese carriers were built shaped their capabilities in ways that extended beyond the ships themselves. American shipyards in the 1930s were transitioning from Depression-era stagnation to rearmament, a process that brought thousands of newly trained workers into the industry. These workers learned modern construction techniques, including welding, prefabrication, and modular assembly. By 1941, American yards could produce carriers faster and more efficiently than any nation on Earth. The techniques developed during the construction of the Yorktown-class carriers were refined and applied to the Essex class, which entered production in 1941. The first Essex-class carrier, USS Essex herself, was laid down in April 1941 and commissioned in December 1942, a construction time of just 20 months from keel laying to commissioning. Subsequent ships in the class were built even faster as yards implemented assembly line methods borrowed from automotive manufacturing. Japanese shipyards, while technically proficient, operated under constraints that limited their output. Japan's steel industry could not match American production, forcing careful allocation of materials. between naval construction, merchant shipping, and military equipment. Specialized components like reduction gears, turbines, and electrical systems were manufactured by a small number of firms whose capacity could not be rapidly expanded. Labor was skilled but limited in number, and training new. Workers took time that Japan did not have once the war began. The result was that Japanese carrier construction, while producing excellent individual ships, could not scale to meet wartime demands. Japan completed only 6 fleet carriers between 1941 and 1945. America completed 17 Essex-class fleet carriers in the same period, plus 9 Independence-class light carriers and dozens of escort carriers. The belief that American carriers were floating scrap, vulnerable to Japanese superiority, was not entirely baseless. American pre-war carrier designs did have flaws. Lexington's loss at Coral Sea demonstrated the dangers of inadequate vapor management. Early war damage control procedures were refined through painful experience. But the fundamental design philosophy, that carriers must be engineered to survive damage, proved sound. The openness to learning from failures, the willingness to invest in unglamorous but critical systems like firefighting and damage control, and the institutional commitment to crew training in survivability created a carrier force that could sustain losses and continue fighting. Japan's failure to recognize the importance of defensive systems until too late was not due to incompetence or ignorance. It was the product of strategic assumptions that proved incorrect. Japan believed the Pacific War would be decided quickly, in a series of sharp engagements that would cripple American will to fight. Carriers designed for that kind of war needed maximum offensive capability. Defense was secondary. When the war became a prolonged struggle of attrition, those assumptions collapsed, but the carriers built under them remained in service, and their vulnerabilities could not be corrected except through new construction that Japan's industrial base could not support. The technological disparity between American and Japanese carriers was not merely a matter of engineering. It reflected differing national capacities, strategic doctrines, and cultural approaches to warfare. America's industrial base allowed over-engineering and redundancy. Japan's constrained resources forced choices that optimized for specific capabilities at the expense of others. American naval doctrine emphasized flexibility, adaptability, and learning from mistakes. Japanese doctrine emphasized decisive battle and spiritual superiority over material considerations. When those doctrines collided at Midway, the outcome validated one and destroyed the other. In the decades since Midway, historians have debated the battle's significance. Some argue it was the turning point of the Pacific War, the moment when Japan's defeat became inevitable. Others contend that Japan's industrial and demographic disadvantages meant she was always going to lose a prolonged war, and Midway merely accelerated the timeline. Both views hold elements of truth. Japan could not have won a long war against the United States, but Midway ensured the war would be long by crippling Japan's ability to force a quick decision. The destruction of the Kido Butai meant Japan could no longer project offensive air power at the operational level. Every subsequent battle was defensive or locally offensive, lacking the strategic reach that characterized the first 6 months of the war. The material logistics that supported American carrier operations after Midway demonstrated advantages that went beyond ship design. American fleet trains, the networks of oilers, ammunition ships, supply vessels, and repair ships that supported combat operations allowed carriers to remain at sea for months with only brief returns to port. These auxiliary vessels were not glamorous, but they were essential. Fleet oilers could transfer tens of thousands of gallons of fuel oil and aviation gasoline to carriers while both ships were underway, a technique called replenishment at sea that required precise ship handling and specialized equipment. American oilers were equipped with high-capacity pumps and reinforced hoses that could transfer fuel in heavy seas. Japanese oilers had less capacity and more primitive transfer equipment, limiting their effectiveness. American ammunition ships carried not just bombs and torpedoes but also the fuses, propellant charges, and specialized ordnance needed for different missions. They could transfer ammunition to carriers at sea, allowing continuous operations without returning to base. Repair ships carried machine shops, spare parts, and technicians who could fix battle damage that would otherwise require a shipyard. After the Battle of Santa Cruz, repair ship USS Vestal rendezvoused with Enterprise at sea and worked for 2 days patching bomb damage, replacing the destroyed forward elevator with steel plates, and restoring systems. This allowed Enterprise to remain operational rather than returning to Pearl Harbor for repairs that would have taken weeks. Japan lacked this logistical infrastructure. Japanese carriers were designed for shorter-range operations, closer to bases where they could be resupplied and repaired. When forced to operate at extended distances, they consumed fuel and ordnance faster than supply lines could sustain. Japanese oilers and ammunition ships were fewer in number, less capable, and increasingly vulnerable to American submarine attacks as the war progressed. By 1944, Japanese carriers that survived combat often had to return to Japan for basic resupply because the forward bases lacked the facilities and stocks needed to support them. The submarine campaign against Japanese logistics amplified these disparities. American submarines, initially hampered by defective torpedoes, became devastatingly effective by 1943 once the torpedo problems were corrected. They targeted Japanese tankers and cargo ships, sinking hundreds of vessels that were carrying fuel oil, aviation gasoline, food, and raw materials. Each sinking reduced Japan's ability to support her remaining carriers. By late 1944, Japan had sufficient carrier hulls but inadequate fuel to operate them. At the Battle of Leyte Gulf in October 1944, Japanese carriers sailed as decoys, with partial air groups because fuel shortages prevented full embarkation of aircraft and limited training flights. American carriers, by contrast, operated at full capacity throughout the war, limited only by the availability of trained pilots and the willingness of commanders to risk their ships. The psychological impact of Midway on both navies proved as significant as the material losses. American sailors entered subsequent battles with confidence that their carriers could absorb damage, and their damage control training would keep ships afloat. This confidence translated into aggressive tactics and willingness to engage even when outnumbered. Japanese sailors, by contrast, knew their ships were vulnerable in ways American carriers were not. This knowledge affected decision-making at every level. Commanders became more cautious, unwilling to risk carriers in situations where American admirals would have pressed forward. Pilots flew with the understanding that if they were shot down, their chances of rescue were slim because Japanese surface forces rarely devoted resources to recovering downed aviators. American pilots knew that submarines, float planes, and even carrier aircraft were assigned to rescue duties, improving morale and encouraging aggressive tactics. For the United States, Midway validated carrier-centric naval warfare and confirmed that American carriers could not only survive but dominate in combat. The victory boosted morale at a time when the war news had been unrelentingly grim. It demonstrated that American intelligence, planning, and engineering could overcome initial tactical disadvantages. And it provided a template for future operations: use intelligence to position forces advantageously, accept losses in pursuit of decisive strikes, and rely on superior damage control and sustainability to outlast the enemy. That template carried American forces across the Pacific, from Midway to Guadalcanal to the Philippines to Okinawa. Each campaign grinding down Japanese strength until surrender became inevitable. The engineering choices that determined Midway's outcome began not in shipyards but in the minds of naval architects who had never seen carrier combat. When American designers at Newport News Shipbuilding and the New York Naval Shipyard began converting Lexington and Saratoga in 1922. They worked from assumptions shaped by World War I battleship experience. The priority was compartmentalize, dividing the hull into watertight sections that could be individually sealed to contain flooding. The original battlecruiser designs included extensive subdivision, with hundreds of watertight doors and multiple levels of bulkheads. The carrier conversions retained this architecture, adding hangar deck ventilation as an afterthought rather than a primary design feature. It was only after fire tests in the late 1920s demonstrated that aviation gasoline vapors could detonate with the force of high explosives that designers began incorporating active ventilation systems and CO2 suppression into carrier specifications. Japanese designers faced different constraints. The cargo conversion began with a battleship hull that was broader and heavier than the Akagi battlecruiser, offering more internal volume but less speed. Japanese naval architects prioritized aircraft capacity and launch efficiency, which drove decisions about hangar layout and fuel system routing. The enclosed hangar design allowed for 2 full hangar decks on Akagi and Kaga, maximizing the number of aircraft that could be stored and serviced simultaneously. This doubled the maintenance capacity but created enclosed volumes where explosive vapors could accumulate. Japanese fire suppression systems focused on foam and water curtains rather than inert gas flooding, a choice that proved effective against small fires but inadequate when confronted with the massive conflagrations caused by bomb-induced fuel explosions. The training pipelines that produced damage control personnel in both navies reflected these different philosophies. American recruits entering the Navy in the 1930s spent weeks at Great Lakes Naval Training Station learning basic damage control before ever setting foot on a ship. The curriculum included firefighting with actual flames, shoring exercises using full-scale compartment mock-ups, and flooding scenarios in compartments that could be deliberately flooded and pumped out. This training was not theoretical. Recruits fought real fires with real equipment, learned to handle high pressure hoses in smoke-filled spaces, and practiced sealing ruptures while water poured in. By the time a sailor reported to his first ship, he had muscle memory for emergency procedures and confidence that equipment would work because he had used it. Japanese damage control training emphasized discipline and endurance but lacked the extensive practical component that characterized American programs. Japanese naval recruits underwent rigorous physical conditioning and learned to operate firefighting equipment through demonstration and drill. But they had fewer opportunities to practice under realistic conditions. This was partly due to resource constraints. Japan could not afford to build elaborate training facilities or expend large quantities of fuel and water on exercises. It was also philosophical. Japanese naval doctrine placed faith in spiritual training and the will to overcome adversity, assuming that properly motivated men would find ways to control damage through determination. This worked when damage was manageable, but when fires grew beyond the capacity of small teams to contain, determination alone could not compensate for inadequate systems or insufficient training. The carriers that fought at Midway were products of decisions made years and sometimes decades earlier: treaty negotiations, design compromises, doctrinal debates, and industrial priorities. The battle's outcome was determined not in the heat of combat but in the quiet work of engineers, trainers, and planners who understood that carrier warfare would be won by ships and crews that could survive, adapt, and continue fighting after the first blow was struck. Japan's carriers were magnificent expressions of offensive power, but they could not survive the war they were built to fight. American carriers were less elegant, more utilitarian, over-engineered for resilience rather than optimized for striking power. But they survived, and in surviving, they won. The legacy of carrier design philosophy forged at Midway extended into the post-war era and influenced naval aviation for generations. When the United States Navy designed supercarriers in the 1950s and 1960s, nuclear-powered giants like USS Enterprise, CVN-65, and the Nimitz class, the emphasis on damage control survivability remained paramount. These ships incorporated redundant systems, distributed damage control equipment, and compartmentalization schemes directly descended from the lessons learned when Yorktown fought fires with portable pumps and CO2 systems. Modern American carriers have armored flight decks, redundant power generation, multiple firefighting systems, and crews trained to a level of damage control proficiency that reflects institutional memory of what happened when carriers could not control fires. The Soviet Navy, studying American and British carrier operations, concluded that carriers were too vulnerable to be effective capital ships. Soviet naval doctrine emphasized submarine and missile attacks rather than carrier-based aviation. But when the Soviet Union did build carriers, starting with the Kiev class in the 1970s, they incorporated design features clearly influenced by Japanese failures at Midway, including enclosed hangars and centralized damage control, combined with heavy missile armament intended to destroy enemy carriers before they could strike. The results were ships that looked formidable but lacked the operational flexibility and survivability of American carriers. When the Soviet Union collapsed and Russia inherited these vessels, their operational limitations became apparent and most were scrapped or sold. The irony is that the Japanese carriers destroyed at Midway were, in most respects, excellent ships. Akagi and Kaga were fast, could operate large air groups, and had served effectively for years. Tsuryu and Hiryu were modern designs that incorporated improvements over earlier vessels. Their crews were professional, their maintenance standards high, and their combat record before Midway was flawless. What destroyed them was not incompetence or poor seamanship but a design philosophy that prioritized offensive capability over defensive resilience, combined with operational decisions that left them exposed at a critical moment. Those decisions, to rearm aircraft, to crowd flight decks with fueled planes, to operate without adequate air search radar, were reasonable within the context of Japanese carrier doctrine. They became fatal when American dive bombers arrived overhead at precisely the moment when Japanese carriers were most vulnerable. American carriers at Midway were not invulnerable. Yorktown proved that when she took bomb and torpedo damage that eventually sank her. But the difference was that American carriers could absorb punishment that would have destroyed Japanese vessels and continue fighting long enough to accomplish their missions. That resilience was engineered into every rivet, every pump, every length of CO2 piping, and every hour of damage control training. It was not dramatic or glamorous. It did not win battles by itself. But it ensured that when battles were won, American carriers survived to fight again, while Japanese carriers burned and sank, taking with them the experienced crews and institutional knowledge that could never be replaced. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.